Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and today I'm going to talk about something a little different. This is still a lecture on calculus, my first year calculus series, but I'm not going to talk specifically about integration today, but instead I'm going to talk about a very important type of function known as hyperbolic functions. These are analogous to trigonometric functions, which I'm sure you guys are all familiar with. And you'll see that they have some properties in terms of calculus that are very analogous to the trigonometric functions, also called circular functions. So anyway, let's begin. So, like I said, there's a very strong analogy between these things called circular functions or trigonometric functions, which I'm sure you guys learned in high school, as well as hyperbolic functions. And the analogy, I think that's better to think of trigonometric functions as circular functions, actually. So you probably learned at some point that you can define, the two most basic trigonometric functions or circular functions, if you like, cosine and sine. Cosine of t, t is really theta, t is your angle. Cosine of t is just the x component. So this is a unit circle here. So if you have a unit circle and you have some point P on the unit circle, you probably learn that if t is the angle that the ray that passes from the O, the origin, to the point P on the unit circle, the angle that ray makes with the positive x-axis is usually called theta. Here we're calling it t. And in this case, cosine of t is just the x component of p, and sine of t is the y component of t. And then you can, define the other four trigonometric functions in terms of sine and cosine, tangent, sine over cosine, so on. And you can do kind of the same thing with hyperbolic functions. And here, instead of the unit circle, we have what's called the unit hyperbola. And I guess I should talk about that a little bit. So here, I mean, as you probably know about hyperbolas have two branches. And in this case, we only care about the branch on the right. But just like the equation of the unit circle is x squared plus y squared equals 1, it turns out the equation of this hyperbola is x squared minus y squared equals 1. So the only thing we've changed is the sign, S-I-G-N, of the thing multiplying y squared. And and you might wonder, and then you can define these hyperbolic functions kind of the same way. Might as well still look at this picture. And you could ignore the branch on the left, like I think I already said. So we have this quantity alpha. You might wonder what it is. I think they explain on this slide. Maybe I should just go back to this slide. So here they're just using t for the variable for both. It's probably better to use the same variable. So another way you can think of this angle t in the first picture, the picture of the circular functions, t is just twice the area of this wedge. You probably know that the area of a circle's pi r squared, so the area of the unit circle's pi, but you have 2 pi radians going around. So the area is twice what the no, the angle is twice the area. Yeah, that's right. The area is half the angle in this case. And the same thing's true for the hyperbolic functions. It's a lot harder to compute these areas, but it turns out this variable t we're using to parameterize a point on the right branch of the hyperbola is also equal to twice the area, twice the shaded area in this case. So now we can define the hyperbolic functions the same way. We start with this right branch of the unit hyperbola, and we just mark a point P on that branch. And then in the same way we did for the circular function, we make a ray from O, the origin, to P. And we say that T is twice the area. It's just I mean, you don't really have to worry that much about what T is, but it is twice the area. That's how we're parameterizing the points on this hyperbola. And then once we have that parameterization, we say that the hyperbolic cosine, which we write as cosh of t, is just the x component of p. And similarly, sinh of t is going to be the y component. And you might notice something interesting here. If cosh of 0 is 1, just like cosine of 0 is 1, cosh of 0 is 1, but you probably know that the cosine of every angle is less than 1. The absolute value is between minus 1. Well, the absolute value is always less than or equal to 1. T, in this case, cosine is between minus 1 and 1. But the difference with cosh is actually always greater than or equal to 1. So it kind of behaves in the opposite way as cosine. And sinh, we can define sinh the same way we define sine for the circular function. Sinh is just the y component of p. And sinh of 0 is 0, just like for sine. Because if we're on the x-axis, p is going to be, just on the x-axis, and it's going to be the point um, 0, 1 comma 0. Yeah, the y component is sinh. So that's going to be 1 comma 0. So sinh of 0 is 0. But if t is positive, then sinh t is going to be positive. And unlike sine, which only goes between minus 1 and 1, just like the cosine, sinh in this case can go to infinity. Because this right branch of the hyperbola, remember hyperbolas go out to infinity. So cos and sinh are both unbounded. That's a big difference between the circular functions, the hyperbolic functions. The hyperbolic functions tend to infinity as t gets large. And just like cosine is an even function of t, cosh is also an even function. Cosh, you'll notice, is always positive. It's always greater or equal to 1. But sinh is an odd function. Sinh can be negative. So sinh actually goes from minus infinity to infinity. But anyway, that's how we define cosh and sinh. And like I said, you can define the other 4 hyperbolic functions with the same formulas in terms of cosine and sine. Remember, tangent is sine over cosine, cotangent is cosine over sine. In the same way, hyperbolic tangent is sinh over cosh, and hyperbolic cotangent is cosh over sinh. And then there's 2 more. Secant for the circular function is 1 over cosine. Cosecant is 1 over sine. And similarly, hyperbolic secant, which is SECH, is 1 over cosh. And hyperbolic cotangent, which I actually show here, is 1 over sinh. So that's how we define the hyperbolic functions. And actually, there's nice formulas for them. Another thing that's nice about the hyperbolic functions, they're actually, you can define them in terms of exponential functions. That's the nice thing about it. You can't do that with trig functions, but you can do it with hyperbolic functions, and there's nice formulas for them. So we really didn't need them. I mean, they're convenient. That's why we define them, because they're going to have a lot of convenient properties, as you'll see. But these are just definitions of all the hyperbolic functions in terms of, e to the x and e to the minus x. It turns out you can define them all in terms of, they're just simple rational expressions involving e to the x and e to the minus x. For instance, I think the only 2 you really have to memorize here, sinh x is e to the x minus e to the minus x over 2, and cosh x is e to the x plus e to the minus x over 2. The other is you can derive, because like I said, you can define tangents or sinh and cosh, and if you use that definition, you just get the formula shown here, e to the x minus e to the x over e to the x plus e to the x. And similarly for the other ones, I'm even going to go over the other formulas. You have to be a little bit careful about the domains for hyperbolic cosecant and hyperbolic cotangent. It turns out x can't be 0, because then you would be dividing by 0. And you might want to look at graphs of these. Oh, but I think I should say one more thing. Actually, maybe I'll just go over the graphs first. So here's graphs of the 6 hyperbolic functions, and the first 2 are cosh and sinh. And I think I should talk about cosh first. Cosh is the one in the upper left quadrant. There's another name for this type of curve. It's called a catenary. And catenary is a very important function in mathematics. It actually has a very useful physical interpretation. If you take a string or a rope, if you just attach a rope to two poles, say, and then you leave the rope some slack. So say you have a rope that's 50 feet long, but then you hang the tops, the edges, the ends of the rope to poles that are maybe less than 50 feet apart, say maybe 30 feet apart. Then the rope is going to form this shape. The rope is going to assume the shape of a hyperbolic cosine, which we also call catenary. So you see hyperbolic cosines in nature. Any hanging rope, any hanging chain or hanging string, it's gonna have this shape. And as a matter of fact, when you build a suspension bridge, the suspension cable, before you put the road on the bridge, the suspension cable has a shape of a hyperbolic cosine or catenary. But once you put the road on the suspension bridge, the road is usually much heavier than the cable, and then it becomes more like a parabola once you do that. But anyway, like I said, it's a very useful function. I don't know any specific physical applications of sinh. And you'll notice, I mean, there's nothing I should have mentioned here. Cosh is e to the x plus e to the minus x over 2. And it has two asymptotes that are exponential functions. So if you look at the right part of the hyperbolic cosine, it gets closer and closer as x gets bigger. It gets closer and closer to the function e to the x. So it basically looks like e to the x if x is large, or e to the x over 2, I guess. And then similarly, if you let x be negative and you let x go to minus infinity, it starts looking like e to the minus x over 2. So it looks exponential as you go to plus or minus infinity. Same with sinh, except the only difference with sinh is that this time the asymptotes, the right asymptote is the same thing, e to the x over 2, but the left asymptote is now minus e to the minus x over 2. Remember I said sinh was an odd function. So the right part of sinh looks a lot like cosh. And then here's the other four. I think, what's the one right below cosh? I think C is hyperbolic secant. That one looks a lot like a bell curve. Not quite like a bell curve, but very close. The tails are just a little bit thicker, I think. And then what do we have? We have a hyperbolic cosecant below hyperbolic sine. That's just the reciprocal hyperbolic sine. Like I said earlier, this one is not defined when x is 0. And this one looks sort of like a hyperbola. It's not quite a hyperbola. In this case, the tails are thinner than they would be for hyperbola. Otherwise, it looks kind of like one. I think the hyperbolic tangent, that's the one bottom left. That one I kind of like. That one is what's called a sigmoid. This one looks actually, it's interesting. This one looks kind of like the inverse tangent, except instead of going between minus pi over 2 and pi over 2, it goes between minus 1 and 1. And once again, the tail is a lot thinner here. But that's a pretty useful function, actually. And then the last one's the hyperbolic cotangent. That's probably the one you'll see the least. It's kind of a weird function. Has 4 asymptotes, I guess, or 3. I mean, it has 2 horizontal asymptotes, x equals minus 1, y equals minus 1, y equals 1. So there's nothing from y equals minus 1 to 1. And again, it's not defined when x is 0, so it has vertical the y-axis is a vertical asymptote. It's an odd function. Anyway, that's what the regular hyperbolic functions look like. But then we also want to look at the inverse hyperbolic functions. And I think this is kind of interesting. Just like the hyperbolic functions can be defined in terms of exponential functions, it turns out the inverse hyperbolic functions can be defined in terms of natural logarithms. And these are a little bit hard to derive, but you can derive them from the, it is possible to derive these formulas. I'm not going to do it in this video, but if you want, you can do it yourself. It's not too hard. And you'll get these formulas for the hyperbolic, the inverse hyperbolic functions. And I think that's kind of nice. And you have to be a little careful with these because the inverse hyperbolic tangent and inverse hyperbolic cotangent are only defined when the absolute value of x is, well, I guess the hyperbolic tangent is only defined when absolute value of x is less than 1, and the hyperbolic cotangent is only defined when absolute value of x is greater than 1. Otherwise, all the other four are defined for all x. So anyway, those are the formulas for the inverse hyperbolic functions. Here's graphs of them. And it's pretty easy to get the graphs of hyperbolic inverse functions just from the original functions. You just reflect everything about y equals x, but you still have to worry about the domain. You still have to make them functions. And this is how the domains are defined, or the ranges are defined for these functions. We can't just, for instance, for the inverse hyperbolic cosine, we have to take the upper branch. We can't take the whole thing because then it wouldn't be a function. Similarly for inverse hyperbolic secant. I think the other ones you can use the whole domain actually. Um, yeah, so the other four just do look like the reflections of the the regular functions about the line y equals x. So anyway, that's what they look like. And now, why am I talking about all this stuff? I mean, this is a class on calculus. I haven't really said anything about calculus yet. And I think the main reason we're interested in these hyperbolic functions is because their derivatives look very much like the formulas for the derivatives of the circular functions, or the trig functions, if you like. We just add h's to everything basically. There's only two exceptions here. You have to be kind of careful about the signs, sign. Notice the derivative of cosine is minus sine, but the derivative of cosh is plus sinh. And the only other difference is the derivative of secant is secant x tan x. The writing is tan x sec x. And in this case, we have to add a minus sign. So I think that's kind of nice that you get and these are pretty easy to derive too, just from the definitions. But I think it's kind of nice that we have formulas for the derivatives that look almost exactly the same as the formulas for the derivatives of the circular functions. And this becomes very useful in calculus, actually. And similarly for the inverse ones, you have formulas for the derivatives of the inverse hyperbolic functions that look almost exactly the same as the formulas for the circular functions. And the main difference is you get a plus sign instead of a minus sign. So, for instance, if you look at the derivative of sinh, that's the one on the right, you get 1 over square root of 1 plus x squared. You probably remember the derivative of inverse sine is 1 over square root of 1 minus x squared. This is going to be important when we're doing integrals, by the way. I think this is the main reason I'm mentioning all this. And then you see there's very analogous formulas for the other ones. And so, this will be useful when we do derivatives. A lot of times you end up using hyperbolic or inverse hyperbolic trig substitutions when you compute integrals with these forms. So these are useful things to know. And I guess that concludes my video for today. So thank you for watching. Long live math, and I'll see you guys next time. Bye.